I'm Seth Mollenauer. I lead the Packaging Solutions Applications Engineering team here at Brewer Science.
I'm Amit Kumar. I'm a Senior Applications Engineer in the Packaging Solutions team at Brewer Science.
And these are 5 key questions to ask when selecting a temporary bonding material. One of the first things we like to ask is, what is the preferred debonding method? We can look at methods ranging from laser debond to mechanical debond, thermal slide debond, or even chemical release. From what we're seeing in the industry, most of the leading edge technologies are leaning towards the mechanical and laser debonding methods as the most optimal ways to separate that carrier from the device. So with laser debonding, we typically use a thicker bonding material coupled with a thinner laser release material that absorbs the UV laser, and there's a photochemical reaction that happens resulting in the ablation and therefore debonding of that bonded pair. With mechanical debonding, we're looking at using a thicker bonding material coupled with a thin mechanical release layer to control the adhesion of that bond line so that we can ensure that the wafer pair is going to survive all of the necessary processes while still being easily separated in the mechanical debonder. Another key consideration we need to take into account when recommending a temporary bonding material is what the thermal budget of the customer's process is going to be. Are we going to be on the lower end with maybe a 260C solder reflow, or do we need to be taking into consideration some deposition processes closer to 400 degrees Celsius?
Higher thermal budget is dictated by the different processes. It can be either process driven or chemical resistance needed by the temporary bonding material. Sometimes as the back end of line process gets more stringent, higher temperature stability might be needed. As processing gets more complex, we have seen the need for higher temperature stability for our temporary bonding material. To meet this requirement, we introduce our Versa layer material, which can survive temperatures up to 400 degrees Celsius.
We also need to have a general understanding of what the topography or features of the device wafer look like, specifically with regard to the height of those features. Once we have that information with a standard thermoplastic bonding material, we have an idea of how much material we need to coat in order to protect and bond that device wafer to a carrier. In the case of our more recent Versa layer series of materials, we use a thin thermoplastic layer of material to conformally coat over the device features, and then a thicker curable material that adheres well to that thermoplastic material to survive any backside processing those wafer pairs may be going through. Ensuring conformal coverage of the device features enables a much more robust bond line that greatly reduces the chances of delamination during the downstream processing, resulting in ultimately device failures.
The adhesion is a key property needed for temporary bonding and debonding applications. We want our temporary bonding material to adhere to various substrates like silicon, silicon nitride, silicon oxide. Sometimes we do see seed layers like tie and copper. So our temporary bonding material needs to adhere to all these wide variety of substrates.
We need to ensure that the adhesion both between our materials as well as those two wafers is well balanced to ensure that we can hold that wafer pair together as it goes through the downstream processing, but also to ensure we can have an easy, low force separation after all of those processes are completed. Another thing we need to take into consideration is the total thickness variation of the wafer stack. For optimal performance, obviously, we want to keep that as low as possible. With our Versa layer materials, we've shown over and over again that we're able to get sub 5% TTV through the wafer processing.
TTV less than 5% is important for stacking and adhesion. TTV that exceeds 5% can lead to uneven bonding, which eventually will result into loss of adhesion or delamination issues in the device.
Brewer Science has specifically developed these products to address the dual priorities of throughput and quality in semiconductor manufacturing. With its high throughput and room temperature bonding, the VersaLayer system provides an efficient bond process. Simultaneously, its low warpage, solid thermal stability, and precise bonding capabilities, as well as flexible debond methods, ensure that the quality of the final product is not compromised. This balance makes the VersaLayer system an ideal solution for manufacturers looking to optimize both production efficiency and product excellence in the competitive semiconductor industry.